Hello, this is mathjazz from Almost Cool, and this is I think it's our 8th live stream at this point. Anyway, I have a list of problems that I'd like to share with you, and if you have any questions that you'd like for me to answer on this stream, you can send those to me at mathjazz9@gmail.com, and I will answer them as they come in. We'll delete this and put in the top of the page our email address. Fantastic. So, our first problem is, I think, a limit problem. Let's see. No, it's an average velocity problem. So, this is a multiple choice question. A particle's position is given at times listed in the table below. Here's a list of feet here, and here is a list of minutes. So, over which of the following intervals does the particle experience the greatest average velocity? The only way to really do this is to compute for each of these 5 intervals what the average velocity is. So the average velocity is going to be the change in time, the change in position divided by the change in time. So for example, on the first interval, our change in time is 5 to 0, and our change in position is 10 to 0. So that'll give us the average velocity on interval A. We can do the same thing for all of these intervals. The distance at time 10 is 25, minus the distance at time 5 is 10. We divide that by 10 minus 5, and we'll go through each of these one at a time. The position at 20 is 40, minus the position at 15 is 45. I guess the particle changed directions at some point. And then we have 20 minus 15. This one we have the position at time 10 is 25, minus the position at time 0 is 0, divided by the time 10 minus time 0. And the last one is we have a position of 40 minus a position of 25, divided by 20 as our time minus 10. And we look at all of these, and the largest one is 3. So that means that this interval here, interval B, had the greatest average velocity. So that's not so bad. We can handle this. So let's move on to problem number 2. That was not as desired. Let me take a look here. It doesn't like that defer in that position. There you go. And I'll just have to fix a couple of things. There. And here. Okay, that should fix it. Okay, so let's go on to problem 2. Here we go. We want to compute this limit. So, the way that we compute this limit is we're going to divide the top and the bottom by infinity. Because if we plug in infinity right now, we get infinity over infinity, which is indeterminate. We'll learn about indeterminate forms when we go over L'Hopital's rule. But for now, infinity over infinity is bad. It's not something that we can make a decision as to what the value of it is without doing further exploration. So we start by dividing on the top and the bottom by x squared. So x squared divided by x squared is 1 in the numerator. And then in the denominator, we get the square root of 4x to the 4th plus 1 times 1 over x squared. Like so. Not quite. Put a parenthesis here and here. Let's also defer this. There we go. So we divided the top by x squared and got 1 in the numerator. We divided the bottom by x squared. We're going to have to push this x squared into the square root. Whenever you push a number inside of a root, you have to alter its exponent. You have to adjust the exponent to take into account it going into the root. So to do that, to go inside of a square root, we have to square our whatever we're shoving into the square root. In this case, 1 over x squared. So it goes into the x squared. We have to square it, and it becomes x to the 4th like that. And then we simplify that fraction on the inside of the square root. We end up with, well, 4x to the 4th divided by x to the 4th is just 4. And then 1 divided by x to the 4th is 1 over x to the 4th. Like so. And Mathematica switched the order of the two terms, but it doesn't matter, it's still equal. Anyway, so now we'll let this thing go to infinity. So as x goes to infinity, 1 over x to the 4th goes to 0. 0 plus 4 is 4. The square root of 4 is 2. And 1 over 2 is a half. Like so. Sorry, that's the wrong term. There we go. Okay. So that is problem 2 of our limit questions. Problem 3. Find the domain of f of x equals the square root of x minus 1 over x minus 2 times x plus 3. So there are 3 things we have to check when looking for domains. They are, what is going to make us divide by 0? what is going to make us take the square root of a negative number, and what is going to make us take the log of a non-positive number. That is, square roots can take zeros, but they can't take negatives. Logarithms can't take zeros or negatives. So we look at this and we see a square root and we see a fraction. So that means we have to worry about dividing by 0, taking the square root of a negative number. But we don't see any logarithms, so we don't have to worry about taking the log of a non-positive number. So we will. It's fairly simple at this point. It's even factored for us. We know that if x equals 2, then bad things happen. Or if x equals negative 3. Both of those cause us to divide by 0. So neither of those can be in the domain. We also notice that we can't let x be less than 1. If x is less than 1, then we're taking the square root of a negative number. Because if x is less than 1, then x minus 1 is negative. So square root of x minus 1 is negative. But it can't equal 1. The square root of of 0 is 0. So 0 is fine. Yeah. So the answer to this will just be that x let's see, we want to write that as, how do we want to write this? We go, x goes from 1 to 2 There we go. It goes from 1 to 2, and it goes from 2 to infinity. And this is the domain of our function. There we go. So the domain of this function is from 1 to 2. Anything less than 1 we have to throw out because of we can't take the... Oh, we can actually use 1, though. There we go. So if we plug in 1, we get the square root of 0. That's fine. If we plug in anything less than 1, we get the square root of a negative number. That's not okay. So there's a hard bracket down here at 1. Can't go less than 1. 2 is bad because then we're dividing by 0. Negative 3, well, that's less than 1, so it's already been thrown out since we've thrown out anything less than 1 for the square root. So here is our domain. Our domain is 1 to 2, including 1, and 2 to infinity. Okay. Let's move on to our next problem. I think that's problem 4. There we go. Which of these functions are inverse functions of themselves? So, the definition of an inverse function is that f composed with f inverse of x has to equal x. Um, so it's there we go. Or f of f inverse of y is y. It doesn't matter. It's just whatever gets stuck into our inside function, this variable here, has to be the same variable that comes out. So let's try this. We're just going to plug each function into itself and see if we get back the identity function. That is, we get back just regular x. So for f, if we plug x into x, do we get back x? Yes. Here we go. We're plugging x in to f of x and plugging that into f of x, and we get back x. This is true. So that means that x is, in fact, its own inverse. And those are the types of functions that we're looking for right now. And Mathematica still thinks that x has a value of 2. Anyway, g of x is going to equal 1 over x. I plugged g into g, and I get this. But dividing by a fraction is the same as multiplying by its reciprocal. So this g of x equals 1 over x is the same as just x. Let me use y's for now because I don't have the time to get rid of x's value of 2. Well, maybe I do. Let's see. Let's pull this up. Valuation. Quick kernel local. Yes. We go back to the code and we execute it. There we go. So g of x equals x. And that's exactly what we want. Now we check h. So if we do h of x, h of x, that is equal to the cube of the cube of x, which is equal to x to the 9th, which is not equal to x. There we go. So since it's not equal to x, that means h is not its own inverse. Okay. So that's good. So f and g are inverses of themselves, but h is not. And that's the answer to that question. Problem 5, I think, is what we want next. Use the definition of derivative to find the derivative of the square root function. Okay. So, math form. Well, the definition of derivative is the limit as x goes to, as h goes to 0 of f of x plus h minus f of x all divided by h. Like that. This is the definition of derivative. So, plugging in square root of x for this, we get, instead of generalized f as our function, we put the square root function here and here, and we end up with this as our result. We're going to have to rationalize the numerator. So we're going to multiply by a very special fraction. It'll be the conjugate of the numerator divided by itself. And the conjugate is what you get when you flip the sign in between the two square root functions. So this is what we're going to get. And it looks like it's a lot more difficult than what we started with, but this is the tool that we want to get to the answer. So when we multiply the top of this out, we notice that the square root of x times the square root of h plus x cancels with the negative square root of x times the square root of h plus x. That is just like this here. This term times this term cancels with this term times this term. So all we're left with is this term times this term, so h plus x, minus this term times this term, which is x. So what we get is h plus x minus x over the square root. Here we go. And there should be an h here. So this is what we get when we multiply our two factors together on the numerator. We get this h plus x minus x. And then the x's will cancel with each other. And the h in the top will cancel with the h in the denominator. So we get 1 in our numerator, and square root of h plus x plus square root of x in the denominator. As h goes to 0, we're left with 1 over the square root of x plus the square root of x, which is really nice. That looks like this. And that is our derivative, and we did it using the definition of derivative, which was one of the requirements in the original question. So now we will go to our next question. It should be number 6. Here we go. If the tangent line of y equals f of x at the point 2, 3 passes through 0, negative 1, what are f of 2 and f prime of 2? Well, this looks trickier than it is. So the tangent line, its slope is going to equal f prime of 2. So what we know is that we have a line that goes through the point 2, 3 and the point 0, negative 1. So we just have to figure out what is the slope of such a line. Well, the difference in y's divided by the difference in x's will give us that slope. So we get 3 minus negative 1 is plus 1 over 2 minus 0. And that is equal to 2. There we go. So that means that our slope is 2 on our tangent line, and the slope of the tangent line is equal to f prime of 2. So f prime of 2 equals 2. Now the other question was, what is f of 2? Well, that's even easier than what we just did. So f of 2, since the tangent line is tangent at the point 2, 3, f of 2 has to equal 3. There we go. So that was worded strangely, but it was not hard. And remembering what the definition or what the interpretations of derivative and tangent line, how you if you're the tangent line at a certain xy coordinate or xy pair, that means the y coordinate is the value of the function at that x value. It's not so hard. It's mostly just remembering what the interpretations of our terms are, not really much hard mathematics. Okay, so let's go on to problem number 7. Prove that the following function has a root between 1 and 2. So this one, this question is asked in a way that makes us think that the correct theorem to use is the intermediate value theorem. And that requires us to know two things. One is whether this function is continuous or not on the interval 1 to 2. And the other thing is there a positive value and a negative value somewhere on the interval 1 to 2? Fortunately, the answer to the first part is yes, the function is continuous. Polynomials are always continuous on the number line. So that's great. Polynomials are continuous everywhere. So f is continuous on 1 to 2. That has to be a closed interval, by the way. The theorem doesn't work on open intervals. You have to have the endpoints be points of continuity as well. So, polynomials are continuous everywhere, so f is continuous on 1 to 2. Now the next thing that we want to do is evaluate what f of 1 is. Well, that's not so bad. It's going to be 1 to the 5th minus 4 times 1 to the 5th minus 1 to the 5th plus 10, 4 times 1 to the 4th minus 1 to the 3rd plus 10 times 1 to the 2nd plus 15 minus 25. And I think that that equals 7 when all is said and done. Let's see. Negative 25, negative 10, 0, negative 1, negative 1, negative 3, negative 4, positive 6, positive 21. I guess this is negative... Oh, I forgot already. Negative 10, okay, 0 to here, negative 4. Negative 4 when all is said and done. F of 1 is negative 4, which is definitely going to be less than 0. The next thing that we want to check is f of 2 positive? Well, let's see. So we get 2 to the 5th is 32, minus 4 times 2 to the 4th, which is 64, minus 8, plus 40, plus 30, minus 25. And so we get 5, 45, 37. 37 plus 32 is 69, and then minus 64 is 5. 5 is definitely greater than 0. So that's fantastic. We have a continuous function who is negative somewhere and positive somewhere else. So that tells us that by the intermediate value theorem, f has a root between 1 and 2. That's exactly what we wanted to know. Okay, so let's check again. Let's do our next problem. Problem 8. Suppose the following relations are true near x equals a. F of x equals that polynomial right here. H equals this polynomial. And g is between f and h. We want to find the limit of g as x goes to 1. So, the way this is worded makes me think squeeze theorem. The conditions, there are two of them on squeeze theorem, are is g between f and h? Well, it is. We were told that in the question. The other part of the squeeze theorem is, does the limit of f equal the limit of h? Now, fortunately, f and h are continuous, so their values at 1 are equal to their limits at 1. So let's just compute what f of 1 is. That's going to be 1 to the 4th, which is 1, minus 9 times 1 to the 3rd, plus 27, minus 9, minus 3, And when all is said and done, this equals, let's see, that's negative 12. Negative 12 plus 27 is going to be 15. Minus 9 is going to be 6. Plus 1 is 7. Hey, this is where the 7 was. Okay, so this limit is equal to 7 because this function is equal to 7 and it's continuous. And now we'll check what h is at 1. H is going to be 21 times 1 squared, which is just 21, plus 7 times 1, which is 7, minus 14. And that is going to be, well, 21. 21 plus 7. This doesn't work. Let's try. Let's try that function. Okay, so when I plug when I plug 1 into h, I get 21 x squared minus 14 equals 7. You know, when I wrote this question, I remembered using the line 22x minus 15. I must not have remembered to change it when I was doing my corrections. That, in fact, this is the problem we want. So h of 1 is going to be 22 minus 15, which is equal to 7. And since the limit on the first function f is equal to the limit on the second function h, that tells us that by the squeeze theorem, the limit of g of x as x goes to 1 is 7. By the squeeze theorem. There we go. Okay, so those are all the problems I have written down for today. Uh, I, let's plot f and h just because we can. After that, we will call it a night, and I hope to see you again next week. Have a great day, and I hope you enjoy studying calculus until then. Here is the plot that we were looking for. So just copy this and copy this. X from, let's say, 0 to 2. That includes the area that we want to see. There we go. See, the line is definitely underneath this blue curve, which is what we wanted. That's a requirement in the squeeze theorem. I think that the other h we had doesn't behave that way. Let's see what that was again. Problem 8. Yeah, let's see. If I graph this h that came from the... Yeah, see, we don't have one function over top of the other. If we were to use these two functions, we would have to take a limit from the right side and from the left side, because technically the squeeze theorem, we'd have to generalize our version of the squeeze theorem. The version that we have, it doesn't work for when the two functions trade places, when one is on top on one side and on the bottom on the other side. But in general, that would work. Like, you need to finagle your version of the squeeze theorem to account for that. The limit would still be the same either way. But that's why we picked the line. The line there was able to be below the parabola everywhere. I guess the line was somewhere over here. Let's add the line in there. 22x minus 15. Yeah, see, this green line here is absolutely beautiful with this blue curve here. Yeah. Well, thanks for watching. I hope that you are enjoying these live streams. I hope that you're enjoying learning calculus. I hope that you all have a great day. Goodbye.